Work I'm going to be talking about today is joint work between myself and Amanda West, who is in the back here. I just want to emphasize that this really is joint work. I'm just kind of the messenger for this. Amanda and I are co-first authors, and if you have any questions about this slide, I really encourage you to talk to us both afterwards. Just didn't really make sense to have two presenters. So, but yeah. And Rabab is with AI for Opt at Georgia Tech, a postdoctoral scholar who has been an absolutely phenomenal influence on this work and really, really helpful. Um, from the title, you can tell that you might be able to tell that this work is about investigating an intersection between energy equity research and optimal power flow research. So for those of you who are familiar with optimal power flow, locational marginal prices are a very important concept, and it basically describes the change in total operating cost for an incremental change in demand. It's an important economic concept in OPF. And in this work, we're investigating how that maps to this energy equity problem. And there's been a lot of academic work recently about a broad swath of different energy equity problems. In distribution systems, we've seen work on electricity rates, PV hosting capacity, and a variety of other transmission problems, capacity expansion, and infrastructure hardening. And this this work in particular is going to essentially focus on one of these common energy equity metrics called energy burden, which is the ratio of someone's household income to the cost of energy that they have incurred for like their electricity demand. And the important gap in the literature right now is that there's not a very clear way to map that metric to an OPF problem. The energy prices which are used for computing this value are actually determined by an LNP, which comes from that OPF problem. And we're going to talk a little bit more about how that actually happens. But I want to give you a quick problem setup, how this works, so we're all on the same page. We're dealing with an N-bus transmission network here. And every bus we're going to model as representing a census tract. And there's going to be n-dimensional vectors of problem data at every point in this talk. We're going to have an average tract income vector S, and we're going to have this retail price model pi and aggregate electricity demands for the entire census tract, this D vector. And as I kind of mentioned verbally before what energy burden is, we're going to introduce a mathematical function for energy burden, which to our knowledge is kind of the first formalization of this concept that has been in the literature. And it's just a vector valued function. It's quite a simple metric. It accepts this demand and this retail price and returns this ratio of like it returns a ratio of the cost incurred for electricity at every household at every census tract, excuse me, to the mean income at that bus. So this is a diagonal matrix of fractions between demand and income multiplied by this retail price. So how do we determine these retail prices? That's kind of the key question here. But before I get into that, I want to describe what we mean exactly by locational marginal burden. So in a similar vein to how you define LMPs, we're going to define an LMB as the change in energy burden incurred at a bus for serving an additional unit of demand at that bus. So it's quite analogous to an LMP. And this sort of graphically depicts what we're talking about. When prior work talks about energy burden in terms of individual households, and we're talking about a transmission level OPF problem. So we're going to aggregate everything in terms of a downstream distribution network to simplify the analysis for now. And this is exactly what I mean by that. We're going to set the retail prices at every household to be the normalized LMP at that census tract's corresponding transmission node. So that's essentially what we're saying by that is we're approximating retail prices with the wholesale price of electricity, which is obviously a simplified model, and that's an incredibly important avenue for future work. But so as a practical example, in Texas, there was a company called Gritty that actually literally did this, exposed their customers to wholesale electricity prices. So this does have an analogy to the real world, but for those of you who may know that, that was actually a horrible idea in Texas for a variety of reasons. And the importance of like making this model more realistic is something that we talk about in the paper. And we actually outlined several different retail pricing models that could be used in this framework generally. Okay, so now the meat of the conversation here. How exactly do we connect this energy equity metric to optimal power flow? So we're going to be working with the parameterized DCOPF problem. This is actually something that has appeared quite a bit in recent literature. And it's for those of you who are not familiar with OPF, I'm just going to give you a quick conceptual rundown. The goal here is for the utility to minimize total operational costs subject to an approximation of the network physics, power balance constraints, line flow constraints, generation capacity constraints. This is a very canonical problem. I'm sure many of you, this is very simple, but I know this is a very diverse conference, so I want to make sure that we cover all the bases here. And we have these problem parameters, this fixed problem data that's input into the problem. We have generation cost coefficients, quadratic and linear, as well as the demand at every census tract. Okay. So how are we doing on time? Fine. Okay. All right. So I want to explain at a high level how our computation scheme for this LMB matrix occurs. So essentially we start with this parameterized OPF problem. The fixed problem data that I mentioned before is input. So this includes like a PTDF matrix, which encodes like topology and network parameters. And more generally, if you're considering an ACOPF problem, you could input something like the bus admittance matrix or I don't know, an incidence matrix, those kind of things. And out of this problem, we compute LMPs, followed by this retail price function that there's a couple of different choices you could have, but we're going to just directly use the LMPs as the retail price. And we apply we apply results from differentiable optimization to actually differentiate the solution of the dual solution of the OPF problem, and thereby differentiate the LMPs. And at the same time, this allows us to generate this locational marginal burden matrix, which is nothing but the Jacobian of this burden function with respect to the demand. Now, if we go back to the definition of this burden function, it's not actually clear how we would compute the Jacobian of this with respect to demand because these retail prices are actually determined as a function of the demand themselves. They are essentially a function of a solution to an optimization problem. So it's quite tricky how you would compute that. And we're going to explain in this work how we do that. Okay. So with basically just applying the chain rule, the implicit function theorem, you can actually come up with a nice expression here for this LMB matrix is what we're calling this. And it's just this Jacobian of this burden function with respect to demand. And just to explain, this is again that demand vector, income vector, PTDF matrix, vector of all ones, and then this Jacobian of the dual optimal solution of the OPF problem with respect to the demand. And then we have this affine term here. And it's relatively straightforward to derive this. It's in the appendix of the paper. All right, so we have a nice case study here with a realistic synthetic network model. It's based on Hawaii. It's from Texas A&M. I highly recommend checking out this data set. It's publicly available. And we mapped this to income data available from the 2021 American Community Survey. And those household incomes were then mapped to the transmission nodes, and we were able to actually just directly test this theory and see what we get. Okay, so the sort of normal energy burden, the generic energy burden function, computing that for this test case immediately already yields some interesting results here. So if we kind of stratify the nodes by number of houses. So like if you fix an income bracket what you end up seeing is basically energy burden inversely correlated with income, and that sort of intuitively makes sense. I mean, when you look at the structure of the function itself, this is the behavior we would expect from the the definition itself. But what was surprising actually is when we go and compute this LMB matrix um, directly for this Hawaii test case, it was kind of surprising to see that actually the diagonal entries of the LMB matrix also follow this same trend. And there's nothing mathematically immediately that indicates that would occur. It's just something that happens from our empirical results. It happens in our empirical results. Um, but the more interesting result that I want to touch on is this next one here, which is that there's no correlation between LMB and population from that we can observe. Like if you look at the color scheme for these scatter points here are based on the number of households, and there's really no clear relationship here. And in fact, we see like this monotonically decreasing relationship between LMB and income as expected. But the the lack of connection between population and the LMB is not immediately clear because that comes directly that is clear in the original definition, but not in this uh, marginal definition. But the next result I want to explain is what we're calling like an LMB to others metric. And what this is essentially the sum of the off diagonal entries of this matrix. So what that is all of the contributions of the change in demand at this particular node to the burden function values of all of the other households in all of the other census tracts in the network. And it's what we end up seeing here actually is that for a particular population density band, the higher income groups will end up contributing more to this off diagonal spectral content of the matrix than right, which is quite interesting. I mean, the interpretation of this here is something that we need to expand on further in other work. But when considering regions of similar average income, areas with lower population density have higher impact on the marginal burden to others. And that's the important takeaway of our empirical results. Customers living in areas with low population density and high income have a higher impact on LMB to others relative to customers living in high population density with low income. All right, I want to conclude the talk here so we can get to questions. The main result here is that we proposed this new metric for kind of unifying this energy burden function with how it would actually be computed in practice with an optimal power flow solution. And we analyzed this matrix extensively. We showed how to compute it in closed form. And we also proposed this LMB to others metric as the sum of the off-diagonal entries of that matrix, which captures the impact of one community's change in demand on the energy prices faced by others. But yeah, so future work, more realistic network. We need better data sets. This is a common problem in all power system work, and we're going to investigate more like this LMB to others metric more closely and have a more fine-grained population income analysis. I'm going to conclude my talk here and pause for questions.